Atoms by themselves don't explain the world you see around you. A single atom cannot form water, build a protein, or create a solid material. The real magic of chemistry begins when atoms stop acting alone and start connecting with one another. And understanding why they do this is what turns atomic theory into real-world chemistry. This is the Learning Studio, where ideas aren't treated as isolated facts, but as connected systems. And now that we've seen how the periodic table maps atomic behavior, the next logical step is to understand the force that actually brings atoms together in the first place. Most people think chemical bonds are just lines drawn between atoms in diagrams, but in reality, they are the result of electrical forces acting at the atomic level. For example, when hydrogen and oxygen combine to form water, nothing is glued together. Instead, electrons are rearranged in a way that lowers the overall energy of the system, making the bonded state more stable than the separate atoms. At the atomic level, the mechanism is simple but powerful. Atoms bond because their electrons interact in ways that create stability. Some atoms transfer electrons, some share them, and some pool them collectively. But in every case, bonding happens because the arrangement of electrons reduces energy and balances electrical forces. This drive towards stability is the fundamental reason atoms stick together. This idea became clear through the work of Gilbert N. Lewis, who introduced the concept of valence electrons, the outer electrons responsible for bonding. He showed that atoms tend to bond in ways that give them stable electron configurations, explaining why chemical reactions follow predictable patterns rather than random combinations. As understanding deepened, Linus Pauling expanded bonding theory by explaining how atoms share electrons unequally and how bond strength, bond length, and molecular shape arise from electron interactions. His work connected bonding to molecular geometry, electronegativity, and material properties, transforming chemical bonding into a quantitative science. Different types of bonding emerge from these same principles. Ionic bonds form when electrons are transferred between atoms with very different electron attractions. Covalent bonds form when atoms share electrons. Metallic bonds arise when electrons move freely among many atoms at once. Although they look different, all chemical bonds are governed by the same underlying rule: electron arrangements that lower energy and stabilize matter. Once chemical bonding is understood, chemistry suddenly becomes coherent. Molecules have shape, materials have strength, reactions have direction, and biological systems can exist at all. From DNA and proteins to plastics, batteries, and semiconductors, every structure in the material world is built on patterns of chemical bonds. And once we understand why atoms stick together, a deeper question naturally follows. If bonds form through electron interactions, then how strong are these bonds? And what determines how easily they break or form? That question takes us directly into the next episode, where we explore chemical reactions and how matter transforms, the process that turns bonds into change.